In this lecture, we'll go over the final controller for this course, the PID, or Proportional Integral Derivative Controller, and go through an entire controller design process from the design step to the simulation and validation steps. As we've done previously, we will use the root locus method during our design process, and we will see the limitations of it, especially for the PID controller. And we're going to implement and validate our design within Simulink to get some numerical results and see how they match the theory. And again, we're going to go an example from beginning of controller design to the end. So first, a quick introduction to the PID controller. This builds on the PD controller that we previously looked at that used a proportion of the error and the derivative of the error to make corrections and to adjust what the input into our plant was. Well, we're now going to add an integral of the error as well. So effectively what we're going to see is that this is going to add 2 zeros into our system by having our controller have 2 zeros and a pole at 0. What this gives us is some additional flexibility from the PD controller, where we're going to be able to choose 2 zeros, which means they could be both real or they could be complex conjugates of each other. And we have a lot more flexibility of the type of controllers that we're going to be able to design and how we can have the behavior of our system be. So there's 2 forms we're going to be expressing the controller. One we're going to be using with the root locus, and one we'll be using when we actually implement this in an actual construction or in simulation. So we're going to see that the controller, starting at the right side first, when we're in the root locus form, we're going to have a Z1 and a Z2 that we're going to get to choose what those zeros are. We're going to put that into the root locus to find what will become KD, that one gain from the root locus. But then if we expand the extreme right and we go to the middle, we're going to find this actually gives us 3 gains. A derivative gain, which we multiply by S, just like we did in the PD controller. The proportional gain, which is just going to be multiplied by the error, again, like the PD controller. And then an integral gain, which we'll divide by S. And thinking back to when we used the I controller in the first lecture, we're reintroducing this integral control. So again, we're going to be putting a gain on the error itself, that's the proportional gain, a derivative of the error, that's the KD, and now also an integral of the error, the KI. Now that we've seen a couple examples of using controllers and testing controllers, let's look now at this general recipe we want to follow for controller design, where we're going to really bring everything together from what we did in Unit 1, 2, and what we're doing now in 3. So really it's on the recipe that I have here, but really we want to start with the model. We need the transfer function of the plant. We need that G0 before we do anything. In these examples, we've been given G0, but really that's the Unit 1 step here. If we're not given G0, we have to derive it using the modeling approaches from Unit 1. So let's say we're at the step we have our G0. The first thing we want to do is choose our controller type. Do we want a proportional controller, a PD controller, a PID? Do we want a lag compensator, or some other design that we didn't cover in this course? But really the first priority of our controller is going to be driving our steady state error to 0, and we want that to be true for any gain or gains that we have in the system. So recall to the first lecture in this unit, there were some times we saw where a particular controller didn't identically drive our error to 0. Or our steady state value to a desired constant. It was dependent on the gain in the system. In general, we want to avoid this. So some controller types, depending on our plant, are not going to be usable because they don't always drive the error to 0. And then within those that do drive the error to 0, then there's different choices that we can make. But that's the first thing we want to check. Does our steady state error go to 0? And we can do this using final value theorem, provided that all of our poles are going to be in the left half plane, which is a requirement for the final value theorem. So again, we are going to check here if y of t is our output, we want to know what does it do as time goes to infinity. Well, from final value theorem, if we know what's happening in the s domain, we can find the limit as s goes to 0 of s times y of s. And what we can do is we're going to find, using that equation in the upper right there, that if we multiply through by r, which in this course we are only going to be using step functions for r, if we multiply through by the r, we want to know, does that limit always go to r, the amplitude of that step function? If this is true, that that limit always will go to the amplitude of our step function, then we've passed this first test. The controller will at least drive the steady state error to 0 given enough time. Now again, depending on the gains we choose, how fast that happens, the overshoot, things like that, those are going to change, but eventually it will drive the error to 0. Right, so now that we know that a controller will work for its main purpose, stabilizing the system, now we want to choose the desired dominant closed loop poles. So this is where we are going to see what's the response requirements of the system. Perhaps there's an overshoot we want to hit exactly, or be a maximum value of some overshoot, or a rise time or a peak time or a settling time, maybe a combination of these that we want our system to have. So what we can do from a theoretical standpoint is take these desired response parameters, and we can from there choose a natural frequency and damping ratio. Again, if we're going to be using the root locus method, we are treating our closed loop system as though it's a second order system, a true second order system. So that's why the natural frequency and damping ratio are going to come into play there. And then if we know the natural frequency and the damping ratio we want our closed loop system to have, well, then we can choose the poles based on those parameters, because we know the poles for a second order system are going to be related to the natural frequency and the damping ratio in this way, if it's an underdamped system, which is what we are usually going to be designing towards. So again, we're presuming that our closed loop system is going to behave like a true second order system. That's not going to be the case. We're going to see in our example in this lecture the weakness of the root locus method, since it's not going to be a true second order system, but at least for an initial design, this is a good starting point. So if we know where we want the dominant closed loop poles to be, the next step is going into our controller design. We want to choose the 0 and or the poles for the controller. So again, like when we looked at the PD controller, we get to choose 1 0 for the placement. For this PID controller, we're going to see that we get to choose 2 zeros. And when we looked at the compensators, we might choose a 0 and a pole. But the methodology is going to be the same. We want the total angle of that g prime, or that root locus transfer function, to add to an odd multiple of 180 degrees. So again, we look at this g prime, which is going to be the controller times the plant without the gain. And we're going to add the zeros of that, and we're going to add the poles of that. And we want it to be 180 degrees, or an odd multiple thereof. If that is true, if the z's and the p's that we pick for the desired pole, where we put that p-value in for s, if that adds to 180, that means that there will be a gain such that we can choose it, and we're going to have our desired closed loop poles appear on the root locus. It doesn't tell us what that gain is going to be, but it will be somewhere on the root locus. At this step, our controller has the zeros and the poles, but we don't know the gain we're going to need for our particular controller. So in the next step, we're going to find what that gain is. We have that g prime, we insert the zeros and or poles from the previous step, and now we're going to make a root locus using this g prime. Right, so this will tell us the k we want to use, so that the dominant poles we selected in previous steps are going to appear on that root locus. If we did everything right in the previous step, the desired pole will appear on the root locus. We just have to find the gain that's going to get us there. All right, so now we have our complete controller with our gain, our zeros and poles, depending on what it looks like. We might need to split that up into the 2 or the 3 gains if we want to implement it in Simulink, or if we want to implement it in hardware. So we might need to find the proportional gain, the integral gain, the differential gain. And then we're going to use Simulink or some other simulation to see what the behavior of our closed loop system is going to be. And again, I'll reiterate that the simulation step and validation step is important, because when we're using the root locus method, we're treating it as though it's a true second order system. When we actually implement it numerically, it's taking into account the extra zeros, the extra poles that we might be adding into the closed loop transfer function that we didn't adjust for when we did the root locus method. So we need to compare the numerical results to what we were doing in theory. So once we run the numerical simulation, now we're going to analyze those results. Right, so from the simulation, we can find what the actual overshoot is, peak time, whatever those design parameters were in step number 2 that we were trying to adhere to. And we can see, are we adhering to them? Are we below the maximum that or minimum that they needed to be? Do we want to kind of be right on them? Are we close enough? If not, and this is going to be the case when we get these more complex controllers, if we're not close enough or we're not exactly to the specifications from the original design, we might need to go all the way back to step number 2 and 3 and redesign our controller. Really what we're looking for is we probably have to change the gain, ultimately the gains in our system, in order to more closely get to the desired response that we wanted from that step number 2. So perhaps the pole we chose was not the best location, the dominant poles we chose. So maybe we reselect those, go back through these processes, change what our root locus is going to look like, which is going to change the gains in the system, and we're going to resimulate it and now again compare it. So we might need to iterate our design several times in order to get to the response that we desire in our closed loop system. And again, why is this the case? Well, from our analysis that we did in Unit 2, we really only know exactly how a second order system is going to behave. If it has a third pole, we'll know generally how it's going to change from that baseline second order system. If there's an extra zero, again, we can modify the baseline system a little bit, but we don't know exactly what that modification is going to do. That's what we're doing in that validation step, is finding exactly how does that third, maybe fourth order system behave? How does that system with an extra zero or 2 extra zeros going to behave? Because it's not going to behave exactly like that second order system. And again, we'll explore this and the issues with this as we go through the example next.